am going to talk about linear algebra. My hope is that you like vaguely remember your linear algebra class, but in my experience, like what's challenging about the comprehensive exam is just trying to remember everything. Like the questions are not meant to be super hard. They are maybe like, I don't know, maybe a little easier than like the final exam questions would be in the course, just because we know that it's hard to remember everything. But so I'm going to try to hit the highlights, and I thought it might be fun. Actually, you should have received from me like about a month ago the previous 2 comprehensive exams, and I hope that you at some point take the time and like go through and try to answer those questions. Like that to me is probably the best way to make sure that you remember how to do the various stuff. I sent you the 24 and 25 like year comprehensive exams. I thought it might be fun for us to try some of those problems, but I didn't want to steal those problems from you. So I, right now, am prepared to give you the 2023 linear algebra section. So these are just so that we could have some questions to work through, but I don't want to steal your thunder in doing the other practice problems. By the way, I would be, if you are like going through the other ones and you see ones that you're not sure how to do, I would be happy to chat with you about it, or you could send me an email. Send me a picture of what you've got so far and ask me how do I do this one. I'd be happy to do that sort of thing, or we could talk in person if you really want to. Anyway, let's. So I thought we could just spend our time sort of going through. There are four problems here. I hope that you have looked at the old exams enough to know the general format. So there's 6 different sections, and you don't have to do every problem. It would be way too long for you to do every problem. I would suggest when you're practicing, you should at least try to do every problem. But when you're doing the test, you want to sort of glance at all the problems and decide which one looks the easiest to do for you. It's not exactly you choose one from each section. You have to do at least one from each section, and then you can do more than one from certain sections. There's somewhat complicated rules which you can see on the first page of those practice exams. It tells you everything. Anyway, the most important thing to review. So I want to go through these 4 problems, but I thought just to get us going, the most important thing that you should know or remember about is how to do the matrix elimination. I hope you remember this. This is sometimes called Gaussian elimination, or the Gauss-Jordan elimination, or row operations. That's that kind of thing. These are all different words, and since I didn't teach your linear algebra class, I don't know exactly what language you are familiar with. But anyway, this is an example. So here is a matrix. This is what we call an augmented matrix because it has like this sort of the bar and then those other 3 numbers over there. Usually an augmented matrix represents the coefficients of a system of linear equations. So this one sort of is meant to represent a system kind of like this, x minus y plus z equals 8, and then the second row means 2x plus 3y minus z equals negative 2, and the last row means 3x minus 2y minus 9 equals negative 9. And by doing the elimination, you can solve the system for x, y, and z. That's the most basic sort of reason that we do the elimination, but actually doing the elimination allows you to answer many more other kinds of questions too. And a lot of these, like these 4 problems that I just handed out, many of them eventually boil down to doing an elimination of some sort. Anyway, let's just make sure that everybody remembers how to do the elimination. So if you're, the general thing, sort of like our goal, is to make it look like 1, 1, 1, and then something, something, something. And if we have zeros everywhere else, this is called the reduced row echelon form, and that, if you can get it to this format, then immediately those 3 numbers are the 3 values of x, y, z, which are the solutions here. This is called the reduced row echelon form. That here is called the identity matrix. You can also sort of not quite go this far and turn it into what we call the upper triangular form, which would have ones here and maybe not zeros here. Either way you can do to solve the system. Anyway, let's go all the way to the reduced row echelon form. So this thing right here, so when I look at this, I see 1 in the corner, and I like that 1 there like it is. And I'm going to use this 1 to eliminate below. So I want to turn that number, the 2 there, into a 0, and also the 3 into a 0. And so let's leave the first row like it is. Of course, there are like slightly different strategies that you can use, and it's fine if you, as long as you end up doing the same things, you should get the same answer. So I'm going to subtract, to get a 0 in this position here, I'm going to subtract 2 times the top row from the middle row. That makes a 0 here. I have 3 minus 2 times negative 1. That gives me a 5 here. And then in this position, I'm going to do negative 1 minus 2 times 1, which will give me negative 3 here. And then this 2, I got to do the same thing. This negative 2 minus 2 times 8, that is negative 2 minus 16, negative 18. All right? If you're lucky, the numbers will be nice. These ones are not so bad, I suppose. All right? And then the last, I'm going to similarly eliminate this 3 in the last row. So I subtract 3 times the top row from the bottom. That puts a 0 here. In this position, I have negative 2 minus 3 times negative 1. That's negative 2 plus 3, which is 1. And then here, I have negative 9 minus 3 times 1. That's negative 9 minus 3, negative 12. And here, I have 9 minus 3 times 8, which is 9 minus 24, 15. Negative 15. Right? I think I did it without screwing anything up. All right. Any suggestions? What should I do next? Yeah?
Could you flip the 2 and 3?
Flip the row 2 and 3? Is that what you said? Yeah. So remember the appropriate sort of like the allowable steps that you can do, they're called the elementary row operations. You can add or subtract one row from another, and that's actually everything that I did so far is of that type. You can also multiply or divide an entire row by a constant, or you can do a row exchange. And to put a 1 in this position, the easiest way would be to exchange these 2 rows. Although you could divide through the middle row by 5, but I don't really want to do that because it screws up the numbers are no longer integers if you do that. So do a row exchange here. Okay. And now I have a 1 in the middle, which I like. I'm going to use that 1 in the middle to eliminate downwards and upwards if I want to get the reduced row echelon form. So to eliminate upwards, let's add the middle row into the top row. So the middle row is going to stay like it is. Adding the middle row to the top row gives me 1 and then 0, and then negative 12 plus 1 is negative 11. Negative 15 plus 8 is 7. Negative 7, yeah. I'm looking on my paper because I am just as likely to screw this up as any of you are. And then on the bottom, we have this 5 here. I'm going to subtract 5 times the middle row from the bottom row. So that's going to be a 0. And then negative 3 minus 5 times negative 12. 5 times negative 12 is negative 60. So it's negative 3 plus 60. That's 57. And I was relieved when I did this ahead of time. When you do this one, you also get 57. Lucky for us. That's negative 18 plus 5 times 15, which is 40. No, 65. Yeah. You get 57. 75. Whatever. I did it ahead of time. Okay. What should we do next? Yeah.
The third row by 57.
Right. I want to put a 1 in this position now, so we should divide through by 57 on the bottom. That makes the bottom row like that. Maybe I'll just copy the others. And then we are going to use that 1 in the bottom row to eliminate upwards in the third column. 1, 0, minus 1. We're almost done here. So eliminating upwards. starting from the bottom row, we can add 12 times the bottom row to the middle row to kill this 12 right there. So it's going to go 0, 1, 0, and then you have to work this out. Negative 15 plus 12 times 1 is negative 3. And then the top row will be 1, 0, and then negative 11 plus, we're going to add 11 times the bottom row into the top row. So that's a 0 here. And then 11 times 1 on the bottom plus negative 7 makes 4. I think I did that right. I hope so. All right. So the solution to my original system, like if you think of this thing as representing this system here, the solution is x equals, if you want to think of it in those terms, x equals 4, y equals negative 3, and z equals 1. All right? This is the solution to the system. Now, that's not all that this elimination tells us. There's many other things that it means. Sort of the fact that I started with this, well, whatever I started with, and I got this format. This is the identity matrix over here. The fact that you can get from here to here means a lot of other things. Anybody remember anything about this? So if I call the original matrix A, let's say that was this 1 minus 1, 1, 2, 3 minus 1, 3 minus 2, negative 9. So this becomes the identity matrix I after elimination. Like if you only focus on the part to the left side of the bar there, it becomes the identity matrix after the elimination. Anybody remember anything else that means? There's like a lot of other stuff that you can say, maybe some other words that you have to remember. About, yeah?
Does it have an inverse?
Yeah, so one thing it means is that A is invertible. This means, it means lots of stuff. It means A is invertible. And if you actually want to find the inverse, I don't actually think that this is part of any of these examples, but if you really want to find the inverse, the general method to do that is you make a big augmented matrix A, and then you put the entire identity matrix next to it, and then you do the row operations until you make identity here, and then something, you get some stuff over here. That stuff is the inverse. So this is the if you had to find the inverse, that's how you would do it. This is A inverse. Maybe I should say, you are allowed to use your calculator on the comprehensive exam, so you should learn, if you don't already know, you should learn how to do this on your calculator. This will save you some time, and you won't mess it up if you know how to do this on your calculator. So I wanted to do just like one example by hand, but yeah.
Can any matrix that we start with be put into eventually the row echelon or reduced row echelon form, or is there ever a time when it wouldn't work?
Yeah, you can, provided that if you're careful about what exactly you mean. Like, you cannot always get the identity matrix,
Yeah.
but you can get. So the definition of the reduced row echelon form is that you have ones coming down here, and so the definition of the reduced row echelon form is the first non-zero number in the row is always a 1. That's this one. Also, every other entry in the column which has one of these ones is 0 everywhere else. And those ones in their position sort of go down and to the right each time. So that is always achievable for many matrix. But you may have like extra columns. Like you could end up with something like, right, like that's also a reduced row echelon form because the ones are here and here, and you just have an extra column so that like there's no way you could get to this just because it has the wrong shape. Yeah, that's a good question. Anybody remember anything else? So this was one thing that this means about that matrix. There's actually several more things that we could say about it just because of the fact that we get the identity there. Anyone else remember anything? You can say something in terms of this, like this thing, we ended up getting the identity matrix, which gives us the answer to the original system. So another thing that you can say here is that any equation, ax equal b, has a unique solution. Ax equal b is kind of the way that you would write a linear system in a matrix format. And like because of the elimination we did get a specific answer for the solution. And that's always going to be true. If you get an identity matrix over here, it means you are going to get a specific answer over here. Ax equal b has a unique solution. Anyone remember anything else in this vein? I had a few more that I was going to mention. How about, here's another one. Ax equals 0 has a unique solution. I should have said up here. Ax equal b has a unique solution for any b. Right? It means in the case of this calculation that we did, actually no matter what numbers you started with on this side of the bar, you would always get some answer here, some specific answer. It wouldn't be, if I change these numbers, it'd be a different answer at the end, but you would still get a specific answer. In particular, this also means that Ax equals 0 has a unique solution. And it is just 0. That is to say, if I actually did this procedure, but I started with all zeros on the right side of the bar, because of the operations you're doing, they're going to stay all zeros all the time. And so what that means is that the only way to get Ax equals 0 is if the x right there is 0. And there's a name for this. Anyone remember this name for the set of all x, which makes Ax equals 0? This is one of the fundamental spaces of the matrix. Yeah,
The null space?
that's the null space. Yeah, so another way of saying that is that the null space, this is also called the kernel. Now that you've taken abstract algebra, you know the kernel means all the things which become 0 after you do the transformation to them. The null space of A is, as a set, it is the set consisting only of the 0 vector. That means the only way to make 0 in the answer is if you started with 0. And that's the same as this. Has a unique solution, and it is 0. All right. There's another word. So something here. There's a word. Anybody remember this? The word for the number of ones that you get after doing this elimination. The number of, these are called the pivots in the row echelon form or the reduced row echelon form. That's called the. Remember?
Not the rank?
It's the rank. Yeah, that's called the rank. So this is another thing that's equivalent to all of this stuff. A is invertible. It means A has, this is sometimes called full rank. Like in this case, the rank is 3 because that matrix is a 3 by 3. So like every single column and row is represented in the rank. So another way of saying that is the rank is equal to the number of columns and the number of rows. In this case, it's just 3 and 3. All right. There's also like spaces. Yeah.
What if it's like the matrix you had up there when it's like 2 right there?
Yeah. So here the rank is 2,
Okay.
and that is the number of rows, but it's not the number of columns. So
Okay.
you don't usually use the phrase full rank in that situation. Yeah. The rank, perhaps you remember, is also equal to the dimension of the column space and the null space. Not the null space, the column space and the row space. And so actually this means that the rank, when I see this, the rank is 3, I also know the dimension of the column space is 3. And the dimension of the row space is 3. One more thing that I'll say here, actually 2 more things. One is about the determinant. What can you say about the determinant? I'm going to write equals or not equals or something. Anybody remember what does the determinant have to do with invertibility? Like I'm saying, the fact that A is invertible tells you something about the determinant. Anyone remember? Yeah?
Does it mean the determinant is not 0?
Is not 0. Yeah, that's actually what the determinant is, like the purpose of the determinant or the reason it was invented. Because the determinant is a number which determines if it's invertible or not. And when the determinant is 0, that means it's not invertible. So if it is invertible, that means the determinant is not 0. And then one more thing I will say is that the columns of A are, this is an important concept, which I hope you remember a little bit, linearly independent. That basically means those columns, there are 3 columns in this example, these 3 of A, and the original 3 columns, when I say they are linearly independent, what that means is you cannot, for example, write the third one as a combination of the first 2 by adding the first 2 together with some coefficients in front of them, a linear combination. All of those 3 columns are independent from one another. It means that no one of them is expressible as a combination of the other 2. And we know they're independent because it went down to this, right? If some of them had been actually combinations of the other ones, they would have fully canceled out here. You would have ended up with something like this. Like if you end up with something like this, that indicates to me the third one really is sort of its own thing, but the middle one is just some kind of combination of the first one, right? Where these leading ones appear tells you about the ways the columns can depend on one another. Yes?
So it's linearly dependent?
Independent.
Another one?
This one, yeah. In this one, the first and the third, if we consider only those 2, they are independent, but the middle one is dependent on the first one.
Okay.
Actually, the middle one is just a constant times the first one. Yeah. Yeah. I think that's all I wanted to say about this. Anybody got questions about this? I hope that these all of these things sound familiar to you. Like I said before, I think you'll have to take some time and review things more than we can tonight, but I hope that. All right, great. Did I have anything else to say? No, let's talk about these problems. So, I already handed these out. This is the linear algebra section from 2023. You received in the email the full exams from 24 and 25, which I hope that you'll have a chance to look at on your own, but I figured I'd give you the 23 problem. So, I thought, in my opinion, I would like to do, I think the easiest one is actually number 44. So let's start with number 44. At least it's the most similar to what I just did. So let's try, this is the 2023 comprehensive exam. Let's do number 44. So this has this matrix here. 1, 2, 5, 0, 1, minus 4, 0. Does anybody have an opinion? Do you prefer writing matrices with the roundy brackets or the square brackets? This is a contentious. Nobody cares? The square? You like the square? Okay. Let's do the square then. Some books are different. Some people can get attached to one or the other way. All right. Okay, this is our matrix. Part A, it says, let T be the linear transformation associated to A. Now this immediately, you might not remember what those words mean and think that this is a really hard question. I think actually this question is not very hard, but you have to keep your wits about you and remember what that means. Anyway, state the dimensions of the domain and the codomain. So T is the linear transformation associated to A. That just means that T is like every matrix you can turn into a function. So I can think of this matrix just as a bunch of numbers in rows, but I can also think of this matrix as a thing which you multiply onto a vector and you get another vector as the answer. So that's what this T is the linear transformation associated to A. That means that T of some vector x is just defined to be A times x. So that's all that the T means. And then you can think of T as a function. It's just a function which is multiplication by A. All right. And then they're asking, state the dimensions of the domain and the codomain. So the domain here of that function T is all of the, x's, which we can put here, right? But of course that means also right there. And the question is just state the dimension of the domain. That just means like, what dimensions should this vector have in order for you to multiply it by A? And this, I hope that folks remember. The question is like, if I were to multiply this matrix by a vector, like how big ought that vector to be? And this is just a thing, I hope you remember how to multiply matrices. You sort of do it with the fingers. I'm writing it again, maybe it's not necessary. Like here, if I want to multiply by something, I don't know, 1, 1, 1, is that the appropriate size to use here? I hope everybody remembers how you would do this if you had to. You do sort of like this with the fingers. You go, wonk, 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 wonk. You go sort of across the rows and down the vector, and you're doing like dot products as you go. You multiply each entry and then add them all up. So actually that is not correct. You need 4 coordinates in the vector in order to make this work. So it has to look like that. Now I don't actually care about doing any particular example, but I hope you all remember the rule about this is something like if my matrix, it has certain dimensions, like this is a 3 by 4. What I have to multiply it by, if I'm multiplying 2 different matrices of any shape, this one has to be a 4 by whatever, 4 by something. And these 2 numbers, in order for this to be a legal multiplication, these 2 numbers have to match. Now in this case, I'm multiplying by a vector, which will be 4 by 1. That is 4 rows and 1 column. All right. And then the answer, I don't really care about calculating the answer, but how big will the answer be? It'll be a vector. What's the size of the answer here?
3 by 1.
Yeah, it'll be 3 by 1. It's sort of like those 2 numbers in the middle have to match, and then the answer is the other 2 numbers. So it's the 3 and the 1. So the answer here will be a 3 by 1. Okay, so anyway, what's the answer to part A? State the dimension of the domain. So the domain is dimension, what do you say? Show me the fingers. The domain is that x there. How big should the vector be? 4, I would say, right? It's just this. The domain, the set of all x's which you can multiply a by, is vectors of dimension 4. So the domain is dimension 4. That's because that's how big these vectors are. And then the codomain, I hope you remember this word from discrete math. The codomain means the stuff that you get as the answer after you do the function. What do you say the dimensions of those vectors are? Yeah, those are dimension 3. Because that's these ones here, right? The answers that you get. That's what the codomain means. And the answers that you get will be vectors of dimension 3. All right. I said that was an easy one, then it took like 10 minutes to explain it. But this is just, the only thing that's hard about this is like the words are a little weird and you have to remember what all the words mean. But once you know what all the words mean, there's not a lot to it. Any thoughts about that? All right, that was part A. Part B, find a basis for and the dimension of the column space. So this, I mentioned this briefly last time. I thought maybe you guys could try this one, and maybe I'll walk around and see how you're doing. What you want to do, I'll give you like the strategy. So this is part B here. We want the column space. Remember, the column space is just the set of all, it's the span of the columns. Another way of saying that is it's the set of all linear combinations of the columns. And the question in your mind should be like, maybe some of these are actually like redundant with the other ones. Or maybe you really do have sort of, well, it's not clear just by looking. Is it possible, for instance, to write this one as a combination of the first two? The answer is, I don't know, maybe. How you would determine that, though, is by finding the row reduction of this matrix. And once you work it out, if you see something like that, that means all 3 of these columns are independent from one another. If you see something like that, it means this one was redundant with the other 2. All right, so see what you think. The question is find a basis for and the dimension of. I'll just tell you what we're going to do is do the row reduction. It's probably good enough just to go to the sort of upper triangular format. You don't have to go all the way to the reduced row echelon form, but whatever you like. And then the dimension of the column space will just be the, well, it's the number of those ones that you get in the result. That's also equal to the rank. There's other words for that, but the dimension of the column space is the number of the, well, those are called the pivot ones in the result. All right, see how you like it. I just want to make sure you all remember how to do the elimination. What's the dimension of the column space? Okay. I give you one more minute, then we'll chat about them.
I got that. I was figuring out how to get back to that last minute.
Yeah, so, okay, is that the same as that?
Yeah.
Yeah, great. So then I did the last row, subtracted 2 times the row.
Oh, God.
And I just get the top row the same.
Okay.
Okay.
Yeah, I got this problem, just not, I gotta make one as a leading one.
Yeah, I think something. When you did this elimination?
Yeah.
I think this should become 0.
Oh, okay, okay.
This would be -6 times, plus 2 times that.
Okay.
Yeah. Still good here? Yeah, great. All right, so in this case, I only went to the kind of triangular form. You could, if you like, I guess there would be only one more. If you wanted to eliminate upwards, you could make this a 0, but that would be the reduced row echelon form. But anyway, this is enough to tell that the rank here is 3, and those ones in those positions are important. What is the dimension of the column space then? It is 3. That means out of, we started with 4 columns total, but actually only 3 of them are kind of like independent from the other ones. That is to say, one of them actually can be written as a combination of the others. This actually, to me, is not a surprise at all. That's because these vectors are each in R3. They're 3-dimensional vectors. So it's not even possible to have 4 different vectors in R3 which are not combinations of one another. Like, since there's 4 of them, there must have been some dependency. Anyway, the dimension of the column space is 3 because this rank is 3. And then it also is asking for a basis for the column space. A basis for the column space means if the dimension is 3, that means like you can pick 3 of these vectors that are actually all different from one another. And a basis would be like, okay, what are those 3 vectors? And I would accept 2 different, well, there's many different bases for the dimension of the column space, but you can basically take these 3 columns here, make a basis for the column space. Or if you prefer, you could take the original 3 columns in those locations, right? The fact that I got these ones here means that those columns of the original matrix are independent from one another. But this one, apparently, this one is actually a combination of the first 2. All right, so a basis for the column space, is, it should be written as a set of 3 vectors, and you could choose the 3 independent columns at the end, or you could choose the 3 columns in those same positions at the beginning. They are equivalent as bases because the row operations preserve the dependencies. So I will just take the ones from the end. The first column, the second column, and the last column. All right, and that other column there is a combination of the first 2. That's a basis for the column space. All right. I hope everyone remembers I haven't actually said the definition of the word basis means it's a set of vectors which is linearly independent and their span is equal to the entire vector space that you're talking about. So in this case, these 3 vectors are independent and the span of these 3 vectors equals the column space. Although in this question, you don't actually have to talk about that stuff because they're not asking you that stuff. But the question could have been like, here are 3 vectors, explain why they are a basis. Then you would have to show that they're linearly independent. You would do this by making a matrix out of them and then showing that they don't. You do the elimination and none of them cancels. And then also show that their span is this column space. Okay, any questions? Yeah?
How would we show that the span is the column space, if that were the question?
Yeah, that's a little weird. I would say, if I were writing these questions, which I am, I wouldn't ask you that. But if somebody asked me, show me that these vectors are a basis for this column space, I would start with this, do the elimination, and then say yes, they are because I just figured that out. It's a weird question to ask the other way around. Yeah. They are a basis for the column space of this matrix, even if you had eliminated that, if like that column just wasn't there at all, or if you had inserted a bunch more other columns. Okay, how about a basis for and the dimension of the null space? Actually, this same elimination allows you to answer most of that question already. Remember, the null space is what you get when you are trying to solve this sort of augmented with all zeros. So, this is part C here. For the null space, like if I just give you a matrix and ask you to find the null space, you do A augmented with a 0 vector, and then do the elimination on that. Now, it's the same elimination as what we just did, but I will just write this again. we're going to get 1, 2, 5, 0, 0, 1 through 0. Sorry, that's not the original matrix. I'm trying to write the original matrix again. It doesn't really matter, but -1, -4, 0, -1, 0, 1, 1. Okay, and I'm going to put zeros here. We do the elimination, and it's going to be all the same steps, and those things to the right of the bar are just going to still be zeros. So we're going to end up with the same triangular form here. 0, 1, 3, 0, 0, 0, 0, 0, 1, 0, okay? And now, in this case, what are you looking for to find the dimension of the null space? There's like a theorem, which is sometimes called the fundamental theorem of linear algebra, that says the rank, which is the dimension of the column space, plus the dimension of the null space equals the number of columns. That's called the rank, sometimes it's called the rank and nullity theorem, that the rank plus the nullity, which is the dimension of the null space, always adds up to the number of columns in the matrix. So when I know the column space, or the rank is 3 here, and there's like one column which is not represented in the rank, that's the dimension of the null space. So it's 1 in this case. Although it's not so hard to just straight up calculate what the null space is, and this is necessary since the question is asking us to find a basis for the null space. So anybody remember how to actually like find the null space once you get to this? This is a somewhat kind of obscure thing that we do, but I'm sure you did it many times in your linear algebra class. I'm going to do the thing with the free variables here. Maybe that rings a bell. So I identify the column which does not have a pivot in it, and I'm going to call that something when I don't know, depends, I don't know what you like to call this thing. I'm going to call it T. The linear algebra books I always use called that thing T. And then you write each row of this equation. Now I'm going to write this as if it was a linear system that came from, you could use like x, y, z's, but since there's 4 of them, I'll just call them x1, x2, x3, x4. And so the last row, row 3, says x4 equals 0. So that's my solution for x4. The second row, row 2, says x2 plus 3x3 equals 0, but I'm going to write x3 as t. So this will be x2 plus 3t equals 0, and I can solve that for x2. x2 equals negative 3t, right? And then the top row, row 1 says x1 plus 2x2 plus 5x3 plus 0, x4, I shouldn't write that at all, equals 0. And then this I can solve for x1. X2 we already said is negative 3t. So this is actually negative 6t here. And then 5x3, x3 is t. And so that's just 5t equals 0. This says x minus t equals 0. And I can solve that for x. I'm talking about x1 here. x1 is t. All right. So you assign a free variable. Every column without a pivot gets a free variable. And if there were more than one such column, I would call them different things, S and T or something like that. And then to sort of write my conclusion, I'm going to package this all together as a vector. x1, and just according to all the things that I just figured out, x1 is t, x2 is negative 3t, x3 is t, because that's just, I assigned this column to be t, and then x4 I said is 0, like so. And this I would sort of factor the t out, and finally that's my basis vector. And so the null space, now if I had like 2 different free variables, s and t, I would have pulled out a s and also pulled out a t, and I would have gotten 2 different vectors here. Anyway, a basis for the null space is just that vector. And that means the dimension of the null space is 1, right? The dimension is how many vectors are in the basis. So it must be 1. All right. And this is a demonstration. They didn't ask you this, but a little follow-up question. Explain how this demonstrates the rank and the nullity theorem. And the rank and nullity theorem says the rank plus the dimension of the null space, that's the nullity, adds up to the number of columns. And it really does, because the rank was 3, the dimension of the null space is 1, they add up to 4, which is the number of columns. So that's the rank and the nullity. Any questions about that one? All right, and the last one, 44, part D. Determine whether or not this vector is in the kernel of T. You have to remember what the kernel means, but actually you know this word from linear algebra or from abstract algebra, but it's the same old thing. The kernel means the set of things which become 0 after you do the function to them. So this is part D. The question is that vector there, V, in the kernel of T? All right, this is equivalent to asking, is T of V equals 0, right? Because that's what kernel means. And remember what T is? Something I wrote a long time ago. T just means this, just means multiplying by A. So the question really is, this is actually an easy question once you unpack the verbiage. The question really is A times V equals 0, right? And that you can just calculate. So A is, the same old matrix we've been talking about. 1 minus 1 minus 4, 0, minus 1, 0, 1, 1. And then the V that they gave us in this problem was 2 minus 6, 2, 1. And then the question is just like, am I going to get 0 or not when I do the multiplication? And maybe we'll just do the first one. Remember how to do the multiplication. You use your 2 fingers. You can use your 2 fingers in your head if you like. And you go across, say, the top row and down this column. So I'm going to do 1 times 2 plus 2 times negative 6 plus 5 times 2. That's 2 minus 12 plus 10, which is 0. So the first entry there is a 0. And if you do this, you got to do that 2 more times for the second row, for the third row. You will see you get zeros for both of those. And so the answer is yes, V is in the kernel of T. Because you got 0, all right? Any thoughts about that one? This, I think, it's taken me a long time to explain every little bit of it, but I think once you know what you're doing, this is, in my opinion, the easy one. I mean, we don't try to make an easy one, but this is the easiest one of those. I think really the game is like, you look at the problems and you just decide like, which of these do I know all the words, which one do I remember what it all means, and that's the one you should decide to do. All right, let's try.
Do you have an extra one of these papers?
Yeah, sure. For your deadbeat friends who didn't come.
Thank you.
Yes. Okay, let's try. I think we should do number 41 next. This one also requires you to remember some words, but other than that, it's very computational based. And I don't want to do any more row reducing by hand. Like I said, you can use your calculator to do it, so you should use your calculator to do it on the test. So A is this matrix, 5 minus 3. See ya, thanks for coming. She doesn't like eigenvalues. She knows all about it. Part A, find all of the eigenvalues. So eigenvalues are actually like super important, but usually we only get to them in like the last week of class in the linear algebra class, and so everybody forgets about them. But they are super important. Anybody actually remember what eigenvalue means? Something about A. It is something about A. So an eigenvalue, well, it's all about this equation here. AX equals lambda x, where lambda is a scalar. So lambda is a number, x is a vector. And this lambda is called the eigenvalue, and x is the eigenvector. what that means is basically they are the vectors and the value. These are vectors. The x is a vector where when you multiply it by the matrix, you basically get the same vector again, but perhaps multiplied by a scalar. And what are those scalars? Those are the eigenvalues. What are those vectors? They're the eigenvectors. And there's just a procedure for finding them, which is, as long as you remember how to do it, it's not all that hard to do. Anybody actually remember how to do it? So the idea is, this here, what you want to do is sort of like solve for x somehow. One way to do that would be subtract everything over to one side. So I'll put ax minus lambda x equals 0. And now I want to somehow like factor out the x. Now you can't quite, you might be tempted to write a minus lambda x like that, right? But actually this is kind of bogus because a is a matrix but lambda is a scalar, and you can't do that. But instead you can do, so it's not that, it is instead this. You turn lambda into a matrix sort of by just making lambda times the identity. All right. And so the x will be the null space of a minus lambda I, because this says a minus lambda I times x is 0, and that's what the null space means. It's the vectors for which you get 0 after you multiply it by the matrix. The problem is we don't know what the lambda is, and so even if we know, like we do know a was given to us, but they didn't give us lambda, so we can't find the x yet until we find the lambdas. So when you're finding these eigen whatevers, you have to find the eigenvalue first, and then you use that to find the eigenvector. So to find the eigenvalue, this means that the null space of a minus lambda I is not trivial. That's because there actually is some vector where when you do this multiplication, you really do get 0. I should have that should be a 0 vector. Sorry, I was writing just the number 0. It means that the null space here is not trivial, which means, i.e., you use the determinant to do this. Determinant of a minus lambda I is 0. All right. If that determinant was not 0, then there would be no vectors which are in the null space except for the 0 vector. But anyway, now finally, this is something which you can just straight up calculate and solve for lambda. So the way to do this is we write determinant of a minus lambda I. I'll write with, the determinant we write with these like absolute value bars. And then what is that? This you can just calculate. A is the matrix we started with. 5 minus 3 minus 6, 2. Minus lambda I. Lambda I is this, right? That's the identity matrix, but multiplied by the scalar lambda. And then you can actually do the subtraction in there. Subtracting matrices, you just subtract the corresponding entries. No problem. So this is 5 minus lambda, negative 3, negative 6, 2 minus lambda. And then you do this determinant, and I hope everybody remembers the determinant of a 2 by 2 is sort of, if it were, A, B, C, D like this, the determinant is AD minus BC. So that's what we do here. And we end up with a polynomial in lambda as, a polynomial where lambda is the variable. 5 minus lambda times 2 minus lambda minus, that's the AD, and then minus the BC, negative 3 times negative 6 is 18. And then remember what I said before, this determinant is 0. So we set that equal to 0, and then you can solve for lambda, because this is a polynomial of degree 2, I suppose. Set this equal to 0, and then solve for lambda. So it's 5 minus lambda, 2 minus lambda, minus 18 equals 0. How do we solve? We have to do the FOIL at the beginning there to expand this into like a normal looking polynomial of degree 2 and then refactor it. So when I do the FOIL business, I get 10 for the constant, negative 2 lambda on the inside, negative 5 lambda on the outside, so that's minus 7 lambda, and then plus lambda squared, that's lambda times lambda. And then I have also the minus 18. And now add this all together. You combine the constants, and I'll write it sort of the usual way around. Lambda squared minus 7 lambda minus 8 is 0. Look at that lambda. It's pretty nice. I would say so. Got that little loopity loops. This is a terrible one, the next one. All right. And then factor, I think lambda minus 8 and plus 1, right? So lambda is 8 and negative 1. This is the answer for part A. Part A just said find all the eigenvalues. That's what they are, 8 and negative 1. Yeah?
How would we take the determinant if it were like a 3 by 3 or 4 by 4?
Those are harder to do, those determinants, but maybe I'll just refresh our memory. Like you should know how to do a determinant like that. You would do it by what we call the cofactor expansion, which would be something like, I don't know if I want to put all, well, I guess we'll do it. If it was something like A, B, C, D, E, F, G, H, I. For anything bigger than a 2 by 2, there isn't like a nice, cute little formula to memorize. Instead, you do what we call the cofactor expansion. I'm going to do it going across the top row. You could also go across actually any of the rows or any of the columns, but it would look like A times this subdeterminant minus B times this subdeterminant plus C times this one. I hope you remember how to do this. So where I'm getting these individual 2 by 2s, and then each of these 2 by 2s you would do the AD minus BC thing. But this comes from, I'm going across the top row here, and associated to the A, I sort of temporarily block out this row and column, and I take the determinant of what remains. That's this. And then I go over to the B, I do the same thing. I block out this row and this column and take the remaining determinant, which is D, F, G, I. And then I go to the C and I do the same thing and I get that one. And you have to alternate the signs when you do this. So it's a very weird procedure. Makes you wonder, whoever came up with this, I actually don't know the answer to that. Gauss maybe? Probably somebody before Gauss knew about this. That's a 3 by 3. If it were a 4 by 4, you do the same thing, go across any of the rows that you like, and then each one boils down to another 3 by 3 to do. It's a terrible thing to do by hand if you really had to do it by hand. Good question though. Yeah, we are not going to do that this evening. Your calculator, I believe, can also do the determinant of a matrix and can also find the inverse of a matrix and maybe can even find the eigenvalues. Anybody know that for sure? I think there's this is, like I said, a super useful thing in like applied applications of linear algebra. And so I wouldn't be surprised if there was an eigenvalue button on your calculator or not a button, but somewhere deep inside the machine, you can probably find a function for that, depending on how fancy your calculator is. Okay, what about, for each eigenvalue, this is part B, find the eigenvector associated to each eigenvalue. So this one, you just have to do this sort of 2 times. Let's do, I have two eigenvalues, 8 and negative 1. Let's do it for 8 first. So for lambda equals 8, I'm going to do a thing to find the appropriate x. Remember, I'm talking about ax equal lambda x, right? This is the same as a minus lambda identity x equals 0. And that you can, now that we know what lambda is, you can just set this up as an augmented matrix and solve it for x. So this looks like I'm going to write a minus 8 times identity, right? This is, my original matrix was, actually, it might be most convenient to just look right here. If you can still see this in your notes. A minus lambda I, I'm going to go here, but use 8 for lambda, because I now know what lambda is. So right here, I'm going to use 8. It'll say 5 minus 8, and then negative 3, negative 6, and then 2 minus 8. Right? That's a minus lambda I, which is negative 3, negative 3, negative 6, negative 6. And you'll see these two rows cancel one another out. But anyway, we are trying to solve a minus lambda I x equals 0. So I'm going to make an augmented matrix of that with 0. And then actually solve this as if it were just like an ordinary linear system. All right. Anybody masters of the row operations? What do you want to do first here? This is a somewhat strange one. I think my first thing would be I want to put a 1 in this position, right? So let's divide the top row through by -3. That makes it 1, 1, 0. All right, and then -6, 0. And then to eliminate downwards using that 1, I would add 6 times the top row to the bottom, and I get 1, 1, 0, 0, 0, 0. So the two rows sort of magically cancel one another out. This is not a coincidence. Actually, if you're doing it right, something weird like that will always happen in this step. It's because the 8 was specifically chosen to make this whole thing possible, right? The 8 was specifically chosen so that a minus lambda I actually does have some vector which becomes 0, and it is necessary to cancel one of the rows in order to make that happen. So from here we do the free variables thing. So I'm going to call that t. So I will say x2 equals t, and then reading the first row, it says x1 plus t equals 0, which means x1 equals -t. And so my solution is x1, x2 equals -t and t. Factor out the t like I do, -1 and 1. So lambda equal 8 has eigenvector x equals -1 and 1. It's the solution of that particular null space thing. All right. Yes?
Is it possible to get two of the eigenvalues that end up being the same, and what does that mean?
That is possible, yeah. So that can happen. You know, you end up with a quadratic in this step, and so it could have only one solution. That we would sometimes call that a repeated eigenvalue. Probably what that would mean, you would only have one eigenvalue. It is possible for that to happen, and in fact, I mean, it can be that there are no solutions to this quadratic, or you could say there are only complex number solutions. That can happen. All right, so that was the eigenvector associated with lambda equals 8. Maybe I will, just for the sake of time, you have to do this again with the other one. It's going to be exactly the same steps. So maybe you could try this on your own later on if you like. Lambda equal -1, you have to do all the same stuff. Of course, you will get a different answer. You will eventually find lambda equal -1 has the eigenvector x equals, I did this ahead of time. 1/2 and 1 is what I got. Yeah, great. All right. So that was part B. Part B said for each eigenvalue that you found in part A, compute a corresponding eigenvector. They said U sub lambda. I didn't call it that, but that's what it is. All right. And then, part C, use your answers to compute a to the power 1,000. I think that this is a really cute trick, although in my opinion, this is kind of an obscure thing that you just have to remember how to do this. And this, in my opinion, is not so easy to remember how to do this. A to the power 1,000. So this is another thing about the eigenvalues is this is referred to as the diagonalization. Sometimes the PDP inverse decomposition, it's basically always written like this. This is just a true fact about a matrix. If a matrix, say n by n matrix, actually has n different eigenvalues, which happened in this case. We have a 2 by 2 and there were 2 different eigenvalues. Then you can write this decomposition, which is also called the diagonalization, where the P, this is the matrix of eigenvectors. You just take your 2 eigenvectors that we got and you put them next to each other in a matrix as columns. And this, the D, so that's the matrix of eigenvectors is the P. P inverse is just the inverse of that, whatever that is. And then the D is the diagonal matrix of the eigenvalues. And there's actually some amount of like, you can write this in different ways depending on what order you put them in. But let's put it sort of in the same order that we figured them out. So my first eigenvector was -1, 1. That's going to be the first column in my P, and then that's going to be the second column, 1/2, 1. So this is -1, 1, and then 1/2, 1, like that. That's the P. The D is the diagonal matrix of eigenvalues, and that is, I did the 8 first, and then the -1 there. So diagonal matrix means you only put numbers on this diagonal bunch of entries. And to get the D, you put the 2 eigenvalues. And you have to be sure that you put them sort of in the proper order. So this 8 is in the first column, and it goes with its own eigenvector in the first column over there. All right? That's the P and the D. What's the P inverse? The P inverse is just the inverse of P. And so this is something you can do on your calculator. Or for a 2 by 2, perhaps you recall, there is a cute little formula for the inverse of a 2 by 2 matrix. It is 1 over the determinant, which is AD minus BC, and then times, anyone remember this little thing? The 2 by 2 inverse, you can sort of swap the diagonals, D and A, and then you negate and leave the other ones where they are. So this is a true fact about 2 by 2 inverses, which probably at one point in your life you had this memorized. I would say for the sake of the comprehensive exam, you can do this on your calculator anyway, so I don't know if you want to memorize that or not, but that's the 2 by 2 inverse formula. So this is P, then P inverse, just doing that, P inverse would be 1 over the determinant here would be -1 minus 1/2. That's -3/2 times that same matrix, but you sort of rearrange stuff and negate stuff. So it's 1 and -1 there, and then I negate these other guys. All right. That 1 over 3/2 you can multiply into the matrix, although for reasons that will become clear in a moment, I'm just going to leave it out here. I will write it as 2/3, but it's actually a little more convenient not to multiply that into the matrix. That's the P inverse. All right. So anyway, how do we do, what is being asked of us is find a to the power 1,000. This is pretty, I actually really like this trick just because if you asked me, if I didn't know how to do diagonalization and you asked me to find a to the power 1,000, the only way to do that is just multiply this matrix by itself 1,000 times, which you would never want to do. But you can, using this diagonalization, P, D, P inverse thing, check it out. A to the 1,000 is, of course, that's P, D, P inverse to the 1,000. But what that means is, it means you write this P, D, P inverse times itself 1,000 times. But this actually simplifies quite a bit. P, D, P inverse. Anybody see what simplifies here?
The
Yeah?
P inverses and the B's are next to each other.
Yeah, right. The P's and the P inverses on the inside will all cancel. The ones, the first one and the last one, they have to stay there. But all of the P's and P inverses on the inside will cancel, and you just get D over and over again. That's just D to the 1,000. P, D to the 1,000, P inverse. And what is d to the 1,000? D to the 1,000 is far easier to calculate than a to the 1,000. That's because d is a diagonal, 8 and -1, and it's just a basic fact of the way matrix multiplication works, that doing a power of the d is just the same as taking 8 to the power 1,000 and also -1 to the power 1,000. This is a very easy matrix to take powers of. So this is, I already know what p is. It is -1, 1, 1/2, 1. That's the p. D to the 1,000 is 8, 0, 0, -1 to the 1,000. But that 1,000 power is actually easy to do. That's the whole point of this diagonalization trick. And then I'm going to write p inverse, and here's where keeping that weird fraction factored out is beneficial. That's the p inverse, right? And now all of this you can just kind of do by hand or with your calculator. This is 8 to the 1,000, 0, 0. -1 to the 1,000, that's just 1, right? Because it's an even power of -1. That scalar in there, actually, this 2/3, you can just like pull that all the way out front. You know, ordinary matrices, of course, you can't rearrange their order when you're multiplying, but scalar multiple you can. So I'll just put the -2/3 out front. All right, this says 8 to the 1,000. And then all of that you can just multiply. I don't know if we need to go through the remaining steps, but I would just multiply these matrices together and you get your answer. Like the first two matrices, maybe I would just multiply the first two first. Doing the fingers here, I go -1 times 8 to the 1,000 and then plus 0. So this is -8 to the 1,000. And then the other entries will be -1 times 0, that's a half here. And then on the bottom, 8 to the 1,000 times plus 0, so that's 8 to the 1,000. And I'm just never going to simplify that, right? It's whatever it is, 8 to the 1,000. And then 0 and 1 is a 1 there, right? So I just multiplied the first two matrices together, and then you have to multiply that result by the other matrix, but that's how you would finish. Equals whatever. This is how you can do big matrix exponents sort of by hand, right? Any thoughts about that? Yeah.
So what are we allowed to do with the calculator? Like, could you just do the inverse on the calculator?
Yes, yeah, you can do the inverse on your calculator. I think for this one, it's a little ambiguous. Like the short answer is you can do whatever you want on your calculator. Although your calculator, I think, can do a to the power 1,000. And so if you just did that and wrote it, we wouldn't give you credit for that. So I mean, if you're, I think usually you will know if you're abusing the calculator. But if you're concerned, like during the test, you can ask, is this good enough? And I'll tell you. Yeah. All right, that was number 41. Great. Let's try. We're halfway done. The other ones, well, I don't know if they'll take as long or not. Let's try number 42 next. So 42 and 43 are a little bit more kind of discrete mathy, a little more like abstract and less computational. Your calculator will not help for number 42 or 43. So let's try 42. They're hitting you with the definitions. W is a subspace. Anybody remember what that means? A lot of these definitions in linear algebra have two parts. Those two parts are addition and scalar multiplication. This is true also for the definition of a linear transformation. So a subspace, these are sets that we're talking about here. V is like the big set. W being a subspace means it is closed under addition and closed under scalar multiplication. So that's your answer for part A. W is closed under addition. And maybe I'll just say like what that means, or if you were really answering this question on the test, that's probably all you need to say, but just because we're gonna have to do this in later parts. What that means is you would, if you were like trying to prove this, you would say something like take U and V in W and then show that U plus V is in W. That's what closed under means. You know, you talk about this like in abstract algebra also. And then also, two parts of the definition of a subspace, it's also closed under scalar multiplication. Right? This is actually, you could say, if you want to be like reductive to your friends when they ask you, what is linear algebra actually about? One thing you could say is linear algebra is all about solving linear equations, systems of linear equations. And that's true, and makes you sound like you're like a 7th grader or something, because they learn how to do that. You could, if you want to sound a little more sophisticated, you could say linear algebra is all about addition and scalar multiplication. That's another general sort of thing that you could say. What it means to be closed under scalar multiplication, you would say take U in W and some constant, a real number, and then we would show that CU is also in W, right? That's how you would demonstrate each of these two properties. And I think we're about to do that. So part B is to actually show that this thing here is a subspace. So let's try that. This will involve proving that it's closed under addition and also proving that it's closed under scalar multiplication. So part B is about this thing that they call X. This is like this is not a normal thing. This is a made-up thing for this problem. A plus B such that A is in A and B is in B. And it says A and B are subspaces. Then when you take this set of all the things which are sums of something from A plus something from B, then that's also a subspace. So our goal is to prove that, we're going to show that this is a subspace. You got to write sort of two little baby proofs here, one for the addition and one for the scalar multiplication. So I begin with closed under addition. And I'm going to write, like I said in red up there, the format of showing something's closed under addition. I take two things which are each in the set. So I'm going to say take, let's say, U and V both in W. And then I will show, it's a good idea to actually write this down as the beginning of your proof. We'll show that U plus V is also in W, right? How do we do that? Well, you would say, first of all, what does it mean when I say U is in W? What does it mean that V is in W? And then hopefully we can add them up and something nice will happen. So I would say, here's my little proof. Since U is in W, what does that mean? Sorry, it's not W, it's X we're talking about. I wrote W, but I'm supposed to be talking about, it's called X. Can I change? Sorry about that.
You keep U and V and you use A and B?
I wouldn't use A and B because here, each thing in X is a A plus a B. So this thing, when I say U is in X, I wouldn't want to call U A because U being in X means U is a plus a B. So don't call it, it's not wrong to call it A and B, but it's very confusing in this problem. You can call it whatever you want, but don't call it A and B because they mean sort of something else here. So I'm going to say since U is in X, that means U is a plus a B. And maybe just because I'm about to also say this about the V, so I'll say since U is in X, we have U is, maybe I'll say A1 plus B1. And then I'm going to say the same for V, but just because I don't want to say A, and it's not the same A and B both times. So also, since V is in X, we have the V is I'll say A2 plus B2. Where we should say A1 is in A, B1 is in B, right? And also A2 is in A, B2 is in B. All right. So that's what it means. And then what we're trying to talk about is U plus V. So we should say, okay, then what about U plus V? U plus V is, I said what U and V are, so we add them together. U plus V, I guess, is A1 plus B1, that's the U, plus A2 plus B2, that's the V, all right? And now, is that really expressible as a plus a B? Anybody, any idea here? I'm gonna do something very simple to sort of be able to think of this as something from A plus something from B. Here it looks like four things together. Yeah?
Is it commutative, so you can swap the A2?
Mm-hmm. Yeah, it is commutative. Like plus is always commutative. So you can do like so. All right? And that, the thing which I helpfully put in the first parentheses, that is in A, because this is a thing, actually I didn't even write this down, but it says it on the paper in the question. It says, assuming that A and B are subspaces. That means these two things which are in A, you add them together, it's still in A, because A is a subspace. So this right here is in A, this right here is in B. So that means U plus V really is a thing from A plus a thing from B. So U plus V really is, if I were to explain this a little more, I basically said the whole thing, but just to say in words, U plus V is a sum of elements from A plus elements from B. So that means U plus V is in X, which is what I wanted to show. All right. That's half of this. That's the closed under addition. Could I have you guys try to do the closed under scalar multiplication? You want to do something similar? It's actually a little easier than what I just did, I think. Scalar multiplication, remember, you choose U to be an X and also a constant, C, a real number.
Do you use the fact that U equals A plus B?
Mm-hmm. Yep. Yeah, you could just say A and B, because there's only one. First one. Yeah, that's great. And how do you know this?
Yeah, I remember that. I guess because, I mean, A1 and B1 are still in sets A and B, and also O and C as well, the reals, A and B are subspaces, so.
That's right. Yeah.
Yeah, that's about as far as I can.
So you have to, you want to see something from A plus something from B. That's what those two things.
Okay.
Yep. I hope you wrote something like this. I'm writing almost the same argument as the first part. It's just this time you choose u, a vector of x, and a scalar, and then you write u as a plus b, and then you multiply by the scalar. You can distribute the scalar, and then CA is in A. That's because A is a subspace, which means A is closed under scalar multiplication. So the CA is in A, and the CB is also in B. So that means the CU is a sum of something from A plus something from B. And so it's in X. All right, and I wrote shewn here. This is my own stupid thing that I write at the end of a proof. I have an old real analysis book from like 1910, which at the end of the proofs it says shewn. It's like an old-timey way of saying I showed it or something like that. So you can write that at the end of your proofs on the comprehensive exam. If you write it on the linear algebra section, I will think it's funny. If you write in the other sections, everyone else will not know what you're talking about. Low battery. Well, we'll just stop when it runs out, I guess. That was 42 part B. Any thoughts about that one? That one, in my opinion, is kind of a hard one, just because this space X is a little weird to get a handle on. Let's talk about, I think we can get through everything. I don't know if my computer will survive, but in our remaining 30 minutes. Part C, give an example of a vector space that is not Rn and a non-trivial subspace. A vector space that is not Rn. If you ask me to give you an example of a vector space, I'm going to say Rn. That's like the standard example of a vector space. But there are other vector spaces other than Rn. What comes to my mind immediately is a vector space. Other important vector spaces would be things inside of Rn, like for instance, instead of all of R3, you could have just like a plane through the origin in R3. That is a vector space. It's actually a subspace of R3, but it's still a vector space on its own. So one answer you could say here would be a vector space that is not Rn. Something like V is something like a plane through the origin in R3. That's a vector space. And then what is a subspace of that? Could you get like even smaller than a plane through the origin? Any ideas? Yeah, a line through the origin. And you could choose, like if you want it to be actually a subspace of that plane, you could pick a line which is also inside of that plane. So I would say my subspace could be a line through the origin. It has to be through the origin in that plane, right? If I want a subspace of the first thing that I talked about. So that's one thing you could do. You could say this in higher dimensions too, like instead of a plane through the origin, you could say like a 5-dimensional thing through the origin in R7 or something like that, if you wanted to be weird about it. Another example, like another important example, I'll say, or something like, something like another important example of a vector space would be something like, say, we call these usually P, like, how about P3? I don't know. This is the set of real polynomials of degree less than or equal to 3. Those make a vector space because if you add two polynomials together, you get another polynomial of the same degree. Actually, if you add two polynomials together, it's possible to decrease the degree if you cancel out the highest degree term, but you can never increase the degree. So that's why it says less than or equal to 3 here. And then what would be a subspace of that? Anyone think of a subspace of that? So this is like the V, the bigger one. What could be a smaller? Yeah, something like P2 or P1 is a subspace of P3. So, right, that's just the polynomials which happen to have degree 2 or less. Oh, you know what? I happen to see, this isn't mine. This is a Nintendo Switch power plug, but it's going to work on my computer. Why did somebody bring this to this classroom? I don't know. stay as long as we like. We're not going to stay past 8. They told me this should go until 8, so it's not going past 8. P2, yeah, that's a subspace. I got one more example that you could say for this, or these are just other examples of other kinds of vector spaces that are not just Rn. The set of all, I would call this maybe like M 3 by 3. This is the set of all 3 by 3 matrices. That's a vector space. Because any two 3 by 3 matrices, you can add them together, you get another 3 by 3 matrix. You can multiply by a scalar, and you get another 3 by 3 matrix. And then, what's a subspace of that? I have to think about like some particular type of matrix. You could, and there's a lot of things that you could say about that, but one example of a subspace, so that's the V, right? The W would be a subspace. You could take something like the set of all, upper triangular 3 by 3 matrices. That makes a subspace. The important property is that if you add them, it's closed under addition and scalar multiplication. So if you add two upper triangulars, it's still upper triangular. Remember, that means that upper triangular means it's got something, and all zeros down there. But these are non-zeros. This is what I mean by upper triangular. Sorry, the dots look kind of like zeros. I shouldn't have used dots. But anyway, what I'm saying is such matrices are closed under addition, because if I add two matrices of this format, then the result is also of this format. And same with scalar multiplication. So that makes a subspace. Those are all the examples that I could think of. There are others, but this is what came to my mind. Vector space that is not Rn. All right? Okay, let's try part D. For each of the following subsets, prove the given set is a subspace. So this one also is about showing that it's a subspace. Now this one, I think whoever wrote, I didn't write this exam, but I think, I'm going to guess it was Professor Rafalski. I'm not sure why. This to me looks like a Rafalski type question. I don't know why. I've never seen him do linear algebra, but so this is part D. The following subsets of R12, is it a subspace or not? Let's do part 1. It is all vectors in R12. So here W is vectors in R12 with the 10th coordinate equals 0. Show that it is a subspace, or explain why it's not a subspace. I think this one is a subspace, and I would say for this one, I would write my proof almost entirely in words. It's a real pain to write down, like in a formula, a vector of 12 coordinates where the 10th one is 0. But what you should be thinking of is, if I take two vectors that have 0 in their 10th coordinate and add them together, does the result also have 0 in the 10th coordinate? And the answer is yes, it does. And that means that it's closed under addition. So I would say, first of all, it is a subspace. So to show that it is closed under addition, I would say if U and V are both in W, then what that means in words, U and V have 10th coordinate equals 0. And so what about U plus V? Well, when you add them up, the 10th coordinate is still 0, because it's 0 plus 0. U and V have 10th coordinate equals 0, so the 10th coordinate of U plus V is 0. So U plus V is in W, which is what we need to show in this part, right? That's the addition. And then scalar multiplication, maybe I'll just say it out loud. Smalt is the same, but you would write similar words to this. You would say if U is in W, that means U has 10th coordinate 0, and then I multiply by some scalar. it still has 10th coordinate 0, because if I choose some scalar c times u in the 10th coordinate will say c times 0. You get 0 again. So that one is also closed under scalar multiplication. Right? What about part 2? The set of vectors whose 11th coordinate is 11. Could you just write like the same proof? I mean, it's 11 instead of 0 here. Any thoughts about that one? Does the same argument work? When you add up two of these things, does it still have the same property? Anybody got an idea? Like the reason the previous one worked is because, you know, if you were to write out, it's basically a bunch of stuff and then a 0 and then some other stuff. But if I add that with the same kind of a thing, the result still has that 0 in that spot, right? What if instead of 0 it were 11? I think it's not going to work then, because if you take something with an 11 and another thing with an 11, they don't give you an 11 when you add them up. They give you a 22, all right? So the answer here is it is not a subspace. You could give, if you like, give a specific counterexample, would be just some vector maybe with all 11s. Then when you add that to itself, you get something with all 22s, and so it's not going to be an 11 anymore. But I would just say not a subspace, since 11 plus 11 is not 11 anymore, right? So not scalar, addition messes up that coordinate. Right. If you add the two vectors together, you're not going to get another vector of the same type. I know it's getting late.
No dinner.
Yeah. I hear that. All right. You want to do the last one? We've done 3 out of 4. Let's do the last one, at least for 15 minutes or so. Okay. The last one is about linear transformations. This is number 43. Linear transformation. First, so part A says define what it means to be a linear transformation. Linear transformation is about a function, but again, it just means that something about addition and something about scalar multiplication. So T is a linear transformation. Means that there's, you know, the two properties are the addition property, which says T of u plus v is T of u plus T of v, and the scalar multiplication property says constant times T of u is T of constant times u. If you're ever in doubt about these definitions, it's probably addition and scalar multiplication. In linear algebra, that's sort of what everything is about. All right. Sorry, my pen is getting messed up here. The way to fix it is to do that. It'll be great now. Okay, that's the definition of linear transformation. Part B, show that this is a linear transformation. So part B is we have this function, t of xyz equals 2x plus y t cubed plus z t plus y plus z. And our job is to show its linear transformation. All right. We have to prove each of those two properties, and you just have to do two separate things. Maybe we'll just do the first one just because we're running out of time here. But we prove the addition property. So you have to, and this is a pretty standard or straightforward calculation. You just have to sort of grind it out. I am going to show, we'll show that if you take, remember what the property is up there? You add two things on the inside of the t. That's the same as adding sort of on the outside. So I'm going to say two things on the inside. I'll call them x, y, z, and maybe x prime, y prime, z prime. You gotta just like call them two different things. And what we need to show is adding on the inside is equivalent to adding each one sort of separately on the outside, like this. All right. And how do we prove that? I would say just write out what the left side is, write out what the right-hand side is, and hopefully they're the same. It's just a matter of calculation. So I'm going to write out the left-hand side first. All right. This one means you add them up first and then plug into the formula for the function. So I'm going to first on the inside add. It's x plus x prime, y plus y prime, z plus z prime on the inside. And then plug that into the function which you see at top. This is a little complicated, but I am using this formula here where instead of x, I have x plus x prime. So I'm going to go 2 parentheses x plus x prime plus y plus y prime. I'm plugging in, instead of x, I'm using x plus x prime. Instead of y, y plus y prime, etc. Okay, that times t cubed plus z, I'm using z plus z prime, t plus y plus y prime plus z plus z prime, like that. All right, that's the left-hand side of the formula I'm trying to prove. And now separately I'm going to write the right-hand side, and hopefully it'll be the same thing. And then that'll do it. So we got that, and also we got t of x, y, z plus t of x prime, y prime, z prime. This one maybe is a little easier to do. You just directly plug into the formula. T of x, y, z is exactly what's written at the top there. 2x plus y t cubed plus zt plus y plus z plus t of x prime, y prime, z prime. That is just the formula at the top, but with primes for everything. 2x prime plus y prime t cubed plus z prime t plus y prime plus z prime. All right. And now what I'm trying to see is that that stuff is the same as that. Are they really the same? You see how could we make this look like that? I think they really are the same. Like, for instance, I have the coefficient on t is z and also z prime, but I can, add up those. You sort of like regroup the like terms in this polynomial, right? The t cubed term, so let's just do it. The t cubed term here would be 2x plus y plus 2x prime plus y prime. That's the t cubed term. The t term is just z plus z prime. And then I suppose the constant term, like the part with no t's, is y plus z plus y prime plus z prime. And that really is the same as this right here. If you were to distribute the 2's and rearrange the terms a little bit, that's the same as this. So I will say this here and that, they are the same. All right. And so we have shown the addition property. Right? That's half of it. You also need to show the scalar multiplication. Maybe I'll leave that. It's a very similar kind of basic calculation. You need to show that constant times t of x, y, z, this one's a little easier, I think, is equal to t of constant times x, y, z. So again, you just sort of plug everything in. I would suggest you just calculate each side separately, and they will be the same. All right, that's how we show. So that was 43b. Show that it is a linear transformation. It really is. All right, I think we can do this before 8 o'clock. How about part C? Going hard here. Prove that the above linear transformation T is 1-to-1 injective, or else show why it is not. So this one, you have to remember a little bit from discrete math. I hope you remember how to prove something is one-to-one. The standard way to prove something is one-to-one is you say, you sort of assume, if I'm just talking about like an ordinary function, you assume f of x equal f of y and then show x equals y. This is how you prove something is one-to-one. You assume that the two values after you do the function are equal, and then you show that that means the original 2 points in the domain are equal. And so we can just do that with this somewhat weird function, but it's possible. So again, I have to choose 2 different things. I'm going to use x, y, z for one of them and x prime, y prime, z prime for the other one. So I'm going to say we assume t of x, y, z equals t of x prime, y prime, z prime. And then our goal is, I mean, maybe it's not true, like they didn't even tell us if it's true or not, but what we would like will show that x, y, z equals x prime, y prime, z prime. I'll just say, or not. I mean, maybe they're not equal, in which case we'll find out when we try to show it. All right. So what does this mean? T of x, y, z equals t of x prime, y prime, z prime. We just plug into the formula for t. So t of x, y, z was 2x plus y t cubed plus z t plus y plus z. I think that's right. All right, that's the left side, equals the other one, which has all the primes, 2x prime plus y prime t cubed plus z prime t plus y prime plus z prime. All right. Each of these are polynomials on the left side and the right side of the equal sign. They are polynomials. If those 2 polynomials are equal, it means their coefficients one by one must be equal. So, for example, it means that this coefficient on t cubed over here must equal this coefficient on t cubed. So I can say, I can actually turn this into several individual equations concerning the coefficients, right? You equate the coefficients on the like terms. So that's the t cubed coefficient. There's also the t coefficient, which is on the left z, and on the right z prime. Actually, when I see this, I'm feeling good about this actually, because that's part of what we need to show these are equal would be z equals z prime. So we already got that one. And then the last one, y plus z equals y prime plus z prime. So we have already shown z equals z prime. That's good. Is it possible to show that y equals y prime from all of this business? I would look at the last one. It says y plus z is y prime plus z prime. But if we already know z equals z prime, then you can change this z into a z prime and then they'll cancel. So here, actually, sort of if we take these 2 together, we can say y plus z prime equals y prime plus z prime, right? Because z and z prime are the same. Cancel the z primes, you get y equals y prime. All right? And then, is it true that x equals x prime? Yes, because you can do the same kind of a thing from there, right? So once we know y equals y prime, using that in the first one, we can cancel these y's on the other side, and then I'll say 2x equals 2x prime, and so x equals x prime. So I'll just say, similarly, x equals x prime. All right, and so altogether, here, here, and here, we have shown indeed x, y, z as a vector is the same as x prime, y prime, z prime. So it is one-to-one. All right. And we got 6 minutes left. I know it's getting late. Prove that it is onto surjective, or else show by example why it is not. Part D. Onto. What that means, remember what surjective means, what onto means. So here's our formula. This is a function they said at the beginning of part B here, they actually wrote the domain. It goes from R3, which is this, a three-dimensional vector, and the answer is a polynomial of degree 3. So this is R3 to P3. And when I say, is it onto? The question is, can you actually get any polynomial of degree 3 out of this? Is it possible to get every polynomial of degree 3? Can that be the answer here? Or are there some that you just can never get? Actually, this, you can, just by looking at the formula here, you can tell. It's not onto. Can you see an example of a degree 3 or less polynomial that you just cannot get as the answer here? It has to do with, there's kind of like a missing term. I don't know if you noticed as we were doing this problem. There's a...
Like no t squared.
There's no t squared, yeah. So can you tell me a polynomial that you could never get as the answer to this?
Maybe like the 2x plus y plus t squared plus then the
Yeah,
rest.
yeah. I would say the simplest example I can think of is just t squared,
Yeah,
right?
yeah.
You can't get t squared as the answer, no matter what you do here. So it is not onto. No, and I would say to explain why, you should give a specific sort of counterexample. I would say since t of x, y, z can never equal t squared, or any polynomial which has a t squared in it can never be the answer. And I think we got through it all. I hope that wasn't too fast. You know, this is the kind of thing that you cannot properly prepare just all at once, but I hope this gives you an idea of what you need to maybe go back and look some more at. Right? Thanks for sticking with it.